Hey everyone, it shows that we are streaming now. So we should see, it says it's waiting for me. Should be working now. How's everyone doing in the chat? So you should be able to hear me and see me. Say hey in that chat. What's going on right now? Everyone doing all right? I had a little fun. I found some new packages. So just waiting for someone to see my fun here in the chat. It's fun just trying to figure out. No, we have 9 people watching. So just waiting for somebody to respond, and we'll start doing some questions right here. So, hey, what's up, Colin? Hey, what's happening? I'm gonna think. I had some questions. I know one person sent him some questions, so we want to make sure to cover their questions. So I think, let me make sure. So I wanted to go ahead and, if you have time to review, definition. Oh yeah, okay, cool. So we'll maybe start with those. So hey, what's up, Cooper? What's up, Lou? What's up, Henyo? What's up, Riley? Good to see everyone here in the chat. We got 13 people. You know, here's the thing. Statue One's got 1,000 students. We only had like 30 people watching. I was like, oh my gosh. But hey, it worked. I think because they can watch their Kahoot later. But you guys are going to drive this review. You guys are going to tell me what to do. And we can just have this cow say whatever we want. We don't even have to do a cow. We can make it a cat right here. Let's just, because this is going to make no sense anymore. We're just going to have the cat say, so that just changed to a rainbow cat right there. So just, you know, Brian finds random package in R to make animals say things. That's cool. So, and then you can do things as long cat. You do a long cat. There you go. There's our long cat right there. So, little fun package right here. So, you know, you can do anything with R code. Maybe that's the person who, oh, it's like a little meme. But anyways, let's start writing our review file for the exam right here. We're going to clear out the bottom console right here. Start with a nice clean bottom console. Let me make sure you guys know, if you are doing your take-home portion, which you should be doing, do Sunday night at 11:59 p.m. And let me do this. I definitely know a lot of these names. Let me make you guys mods of the channel here. If we have anything crazy happen, you guys are my mods, and you guys and gals can go ahead and stop any of the person trying to, you know, do craziness in the chat. You can time them out, you can ban users and all that good stuff. You're now mods on my channel. So with this in mind right here, let's start out with a review question that someone asked, and the review question is, what's the difference between reference and indicator variables? We got survey 10 open right now, one of my favorite ones to just kind of learn with, and if you understand it kind of normally, you can. And I'm going to do something weird right here. I'm going to do it this way. You'll see why in a second. I'm going to predict height. It doesn't have a capital. It does. Try to remember here. From handedness. Now, someone's going to be like, wait, Brian. Wait. You've got an error in your code. Do I? Well, it ran. Let's see what's going on here. We're talking about indicator variables here. And if you notice, I'm going to have indicator variables. And I'm going to put this basically up here so we can see a lot of the output on the screen at one time. So what we have going on right here is indicator variables. Now, what is the reference level for handedness and why? I want to see those answers in the chat. You guys got me. You got my back. Pretend this is the test. Be like, what is the reference level? And remember, you can always send me those questions and I might use them. So ambidextrous, Emerson, you are right. It is ambidextrous because ambidextrous is first alphabetical. Ambidextrous is first alphabetical, thus it is the reference level. Things you see right here are indicators. The variable itself is handedness. You can see that in the output right there. The indicators are right and left. The reference level is the first alphabetical. Key right there. Remember, I am first. In reference levels, I am first. Indicators and reference levels, I am first. Logistic, the level of interest, is last. And we'll maybe look at that in a second here. Now, if you notice, I ran GLM, which we didn't do at the start of the class. But if you actually take a look at the way GLM works, GLM is the generalized linear model, and it'll come up here. It's weird. I think it usually pops up there. There we go. One time I saw it pop up and then didn't. The first family it has here, this is what the default is for it. The family is Gaussian, and Gaussian's the normal curve. So if we're doing, you know, the assumptions of normality and all that, we're actually doing linear regression. So by default, it does Gaussian. But wait a minute. We can also change family to things like binomial. And where's the binomial on here? Or it just says look to family for all the different families you can use. So you can always go through this whole thing right here and you can see the different families. So you could have picked family gamma. I don't really work with that much. Or inverse Gaussian or Poisson or quasi-binomial or quasi-Poisson. Truthfully, I know how to use Poisson and inverse Gaussian. I don't know what's going on with those quasis. Maybe I should, but I don't use them. So you can read all about this and you can see the different families. But if I were to put family here, I could put family equals I don't want to do family equals binomial. I want to do Gaussian. So I want to do family equals Gaussian and it works. We don't usually do it this way, but that's normal right here. This code I have, let me do 3 versions of it. This code right here is the same as, it runs the exact same as this code right here because the default for it is to do family equals Gaussian. So that's set as the default, so it doesn't need that argument, which is the same as this code right here, which is the way we learned at the start of the class. Once again, I am using, this is good stuff for the take-home too, I am using these codes this way because I'm predicting a what type of variable. Why am I doing it this way? Now, this is the way we first learned it, which is probably the way a lot of people do problems like this. I'm predicting a what kind of variable, which is the key for why I'm writing it this way. Quantitative, you're right, Emerson. It's quantitative, so we're doing it this way. Now, we can't use the LM for a categorical. If we switch over here to categorical and we change, let's change this to gender. And now gender is categorical. And we run right here, this has to go over to binomial. Binomial means 2 levels, and we can switch it to binomial, and we can take a look at our output. So if you notice now, I've switched it to binomial, and we can run this right here. And what's it being mad at me about? Error in quantile default, factors are not allowed. What did I do? Height, gender, family equals binomial. Did I mess it up? Let's see. So where did I make a mistake? Someone, oh my gosh, you guys see it in the chat, don't you? It's because there you go, I told you. It's always a mistake somewhere, right? So I know, nice job, Cooper. There's a delay in the chat, so you're going to see me solving it here as you put it in, probably. But yeah, there's always a small mistake we can make with code and the GLM. So no, I'm going to make mistakes with code. But you notice, when your code doesn't run, just think about what I did wrong. And of course, LM does not take the argument family equals binomial. I guess it got mad at me right here. It's saying, no, I can't do this. I don't know what's going on. And it might have actually just skipped over it with the LM. We can actually confirm it's not even reading the argument by just putting in something random in the argument. You go right here to this, and you just type in something random. And you can be like, does it even read this right here? And, well, apparently it does read family. Oh, no, because I have the GLM still. I want to see if with LM it just even ignores the argument. And the answer is, if I use it as LM, yep, still looking for family. And so apparently maybe you can do family with LM. It's always things you can learn. Question mark LM and see what it does. But let's take a look at this output right here. Let me clear the screen a little bit. And let's try to do some interpretation. This is where we got to know it like this. We got to know how to interpret the coefficient of height in this model. Go ahead and try to interpret the coefficient of height in this model. Write it in the chat. We'll do that in a moment here, Abel. We'll do an interpretation with interaction. And let me make you a mod for the channel right now. So we need an interpretation for the we need an interpretation for the coefficient of height in this model. Try to do it in the chat. And if you're watching this video over the weekend, you should be able to do this right now. Pause your video, write it down on a sheet of paper, or write it in the chat if you're in the chat right now. This is something that you should be able to do instantaneously. Interpret the coefficient of height for this model. It does take a little bit of knowledge. Remember, we're predicting gender. I have the code on the screen that I just ran. So this is the code I just ran. Interpret the coefficient of height in this model. See, I want to see if someone get in the chat. I'm going to throw big 1,000 pointers out here. Everyone, if you get an answer right, you got to be first. You get the answer right, you get 1,000 points. Great chance to get some last extra credit for the class. So go ahead and interpret it in the chat and pause the video if you are doing it now. These are things you should, don't just wait for my answer, because, you know, if I say it, you might be like, oh yeah, that's it. But you need to be able to do it without me telling you the answer, and that's the key. And so we should see an answer coming here in the chat in a moment. We've got a lot of people I know that will get a great answer here, and it's all right if you get it wrong. If no one gets it, I'll give it to the first person who even took a real stab at it. You can't just say the interpretation's 2. No, that wouldn't count. Riley, I'm probably gonna give it to Riley. Ooh, Riley, there's 2 errors. Oh, no, there's only one, but it's not even that big of an error. Riley, I would give you 100% on this. Sorry, I thought I saw something else, but I didn't. Riley wrote, two otherwise identical individuals who differ in height by 1. The individual who is taller is more likely to be male. And because remember, in this, level of interest is male. If we go to levels, so we can go here, levels, survey, and I'll mention what the small thing is. Maybe you see it, Riley, but you got the 1,000 right there. The last is male, so the level of interest is male. We can even confirm this by doing a visualization, which you can't obviously do a visualization on the test, but we can confirm that we're predicting male because we see probability male, and we also see two people who are otherwise, that's the small error. It's a simple logistic, and so we wouldn't say otherwise identical. I was going to throw a trick next where I add in like weight right here, and it's just a technicality, but there is no real otherwise identical because there's only one variable in here. But now, two people who are otherwise identical but differ in their height by 1 inch, the individual who is taller is more likely to be male. And it's still the same right here, but if we have a multiple regression, we have to say the otherwise identical part of it. And remember, a lot of this test is very centered around multiple regression. And you might be like, well, that's the last thing we did, right? And that's like what we just started with. How's everything on multiple regression? That's what indicator variables are. Indicator variables, the chapter is how to deal with indicators in a multiple regression. Like I can add in here handedness. So this is, now the regression output has indicators in a multiple regression. So if you look at this right here, this has indicators in a multiple logistic regression. So this right here is a multiple logistic regression with indicator variables. So try to interpret now and this is, yeah, sure. Interpret the coefficient of handedness left. Try it. Pause that video and be like, and I've always mentioned this in class, you're definitely going to have to interpret stuff like this. You have to first ask yourself, and here's a key to these questions, is this logistic or is it just regular regression, like linear regression? And the answer is this is logistic. One, you can see the code. It's using family binomial. That's a good tip right there. And I don't think on the test, I don't think I pulled anything tricky. I just did classic LM. I just wanted to point out this at the start. But when you do family binomial, you are doing logistic. So it's about probabilities. That's what we're predicting probabilities here. So with this in mind right here, interpret I think I said the indicator handedness left, and we should see this appearing in the chat. And let's see who gets these points right here. Try it, give it a shot at it. Remember, you have to be able to interpret these things. You have to be able to be like, okay, how do I interpret the coefficient of handedness left in this right here? And it's very, very key. What does this mean? I'm just going to give a pause. Let me think about what else I can say right here. Well, one thing, and I'll point this out, big hints for the take home. Let me do this while you're figuring it out. There's actually, truthfully, to interpret it, all you need to know is that this has a positive coefficient. That's all you need to know. And then also we're predicting male. With this information, positive coefficient and predicting male, you can actually interpret it fully. You don't need anything else. Great job. Oh, it looks like Will got this one. Two individuals who are otherwise identical. Ooh, oh no, Will, I'm giving you 1,000 and Riley 1,002. Careful. Oh wait, I think Sakas, Paige, I'll call you Paige right there. Paige, I think you might have it. Two individuals who differ in handedness but otherwise identical. The individual who's left-handed is more likely to be male. That looks to be or Cassie, I'll say Cassie right there. That looks to be pretty accurate. Two individuals who are otherwise identical but differ in handedness, where one is left and the other is ambidextrous. Now I'm going to point this out here. Riley got it 100% correct. Because when we interpret an indicator, we must compare it to the reference level. That's key. So if you notice the interpretation there, great job, Riley, got the 1,000, and Paige, I'm throwing you 1,002. You can tell me if you want me to call you Paige or Cassie. Sorry, I thought the Cassie was part of the comment right there. I'll call you whichever you like. And two individuals who are otherwise identical, that's because it's a multiple, but differ in handedness where one is left-handed and the other is ambidextrous. So the individual who is left-handed is more likely to be male. That is key right here because we're comparing this, and I want to make this clear. It's called an indicator because the indicators are compared to the reference. The left-handed and right-handed individuals are more likely to be males. I don't know why. This is not statistically significant. The indicators are not. And to look at the significance of this variable, to wrap it all up, hint, hint, hints, for that take-home, you definitely want to do test equals chi-square. It's in the notes. And right here we have the partial F, which is an effects test, which looks at the significance of handedness. And now we've taken the 2 levels of handedness. Yeah, there's a little bit of a lag. Sorry, it's like 6 seconds. And you got it. Cassie right there. Sorry, Sassy Page. There you go. The right here, the handedness is a 2-level variable. And the 2-level variable right here has 2 levels, handedness right and handedness left. And we would compare those to the level ambidextrous. Now, of course, on the test, you would need to know that. We could check it right now to see the levels of ambidextrous by going here and just going to survey 10 and going here to handedness. And we could see that the reference level is ambidextrous. Sure, let's do some misclassification stuff. Let's do it right here. Let's see how many, we can just go to confusion matrix. I always like it because it sounds like you're confused. And look at our confusion matrix. Boom! Do it right now. Calculate the misclassification rate of this model. So Will, great question right there. Will, figure out the misclassification rate of the naive model, or anyone. Remember, 1,000 points if you get it. Go ahead and give it a shot. What is the misclassification of the naive of your model? We'll do the naive in a second, so get ready for that question. But what is the misclassification rate of this model? Give it a shot. Now, when you think about misclassifications, it's things you get incorrect. And misclassification only applies to categorical variables. So we're using logistic for misclassification. You might be right, Cooper. That sounds about right. I almost pulled the power cord out. It's going to be 79 over 699, so that sounds accurate and everyone's getting it. So it's 79 over 699, which I'll highlight over the output. It is this number over this number, and you can get it. Now what's interesting is you can actually figure it out. I've done this multiple times, but you could make a function right here. Let's just do this super quick. We're just going to take the value of matrix M, or actually, I wonder if, well, we just take in this right here, and we're going to take in whatever someone puts in, and it's going to use it as the confusion matrix. And the confusion matrix is a 3x3, so we need to add together row 2, column 1, and then we need to add to that the confusion matrix. We're going to add in 2, 1, and row 1, 2. So we add in here 1, 2, and then we divide by, and I'm gonna put those in parentheses, and then we divide by the confusion matrix 3, 3. If you notice, that is this number right here plus this number here, divide by this number, and we put this in right here as 3, 3. And what we're gonna do is we're gonna put this inside of a parentheses because these need to be added up together. And then we're going to put this inside of here as a return function, and we're just going to say return this value right here. And let's go here and take a look at this. So this is the beauty of making a function for something, and let's just call this misclass rate. And now we have a function misclass rate, and I can just go misclass rate. Oh, did I not make my function? Oh, there we go. It's misclass rate M, and I already have it stored as M, and there it is right there. There's how you solve it right there. The number of misclassifications, that's correct. And actually, what you're doing there is correct. You see, I can take this. I could just take this function and solve it this way. And what I will get is 79, I believe, unless I'm doing my math wrong. I got 79 because that's how many are misclassified. So if you take the misclassification rate and times it, so we made a little nice function right here. Of course, when you do something, it's a lot better to just, write a code for it, so that way you don't have to do it 1,000 times. And it really wasn't that hard to turn it into a function. I just wrote what I wanted and have it return, and then I could do this right here, and it just gives me this classification rate. I could put if else's in here and actually get the amount if I wanted. Just put in if else, like if someone says, rate, I could do rate equals true, and then if they put rate equals false, it could go to the numeric. Functions are great. They're hugely helpful. This is just a quick, simple function. Just gets me what I want. Takes this number. If you look, this is in position 2, 1. That's why I wrote that. This is in position 1, 2. And this is in position 3, 3. Just add up where we're wrong and then divide by the total. Now, I'm going to make a different function here and call it misclass naive. Oh, this one's more complicated. Oh, no, what I could do is this. Okay. What I need to do here, and let's talk about how this works. So the misclassification of the naive is the following. What we want to do is we're going to make a vector here. This is going to sound confusing. And the vector is going to have 2 values. Let's just say val1. Val1 is this. We have this total over this total right here. Or excuse me. this one over this one. That is 3, 1. I'll explain mechanically what's going on. Like, I hope this way of explaining it. Row 3, column 1. Nope. Row 1, column 3. Let's talk about the misclassification of the naive here and what's going on. So this is the misclassification of the naive. And we'll do p-values here in a second on the interaction. So I'm going to make val 1 right here, and let's talk about what's going on right here. This is the misclassification rate of the naive. The misclassification rate of the naive. So now all I'm going to do is return the max of the vector val 1 and val 2. Okay, so misclassification rate of the naive, let's check it and see if our function works and if we can get the misclassification rate of the naive. The misclassification rate of the naive, oh no, what did I do wrong? Oh, typo, damn you. There we go. There's the misclassification rate on the naive, and let's look at our confusion matrix to confirm this. So confusion matrix, and let's run this, and let's look at the misclassification of the naive. So how would we get the misclassification of the naive? Well, you're going to have to identify, and did I get it right? No, sorry everyone, there's a mistake. Call me out on it. The misclassification rate of the naive is that. So I actually had what we would predict for everybody. The misclassification rate of the naive is the following. I was checking my work and being like, uh-oh, there's a second theoretical mistake. So the misclassification rate of the naive is what? Okay, I want us to think through this. Okay, we've got people who are actually female, and we got people who are actually male. So more people in our survey are what? More people in our survey are what? We got actually female and actually male. More people in our survey are what? More people in our survey are... When you know those answers, make sure to shout them out. Cooper got some points earlier. More people are actually female. Nice job, Emerson. So we would see here that we would say, since more people are actually female, we'd be like, everybody. Hey, typos happen to me too. So we'd say everybody is female. Everybody is female. If we say everybody is female, who would we get wrong? We'd get wrong the people who are actually male. So we'd get wrong the people who are actually male, and we'd get wrong the 313 over 699, which is the same number you see right there. So that's the formula I'm doing, and I wrote something to do it for me. Because all I did was say, find the one that is the minimum, because we would guess this is the amount we get correct. So the complement of that is simply this. And all I did was find both values and find the smaller one, because you get right more often. So kind of a quick trick right there, and you could easily write a function for yourself to just do this. And that's why, once you understand how to do it, usually just write a function and have it do it for you. But you have to understand what's going on. Like, what is the misclassification rate of the naive? And the misclassification of the naive is to assume that everybody is the majority level. Most people, when I see actual female right here, most people are actually female. So I guess everyone's female. Well, then I would get wrong these 313 people who are actually male. Don't go to the predicteds, because the predicteds only deals with the what? The predicteds is the model. That's dealing with the model. So if you're looking at predicteds, that's the model. The naive is the no model. The naive is, it can work sometimes. I mean, it's like, what would be the naive for the Patriots winning a game? Oh, bring some sports into this. What's the naive for the Patriots winning a game? And why would it be that? It kind of, if you understand these things in concepts of life, like why, hey, the Patriots are playing this week. Gee, like Emerson, 1,000 points. And the answer is win, of course. And we didn't say how they'd win. I mean, I don't know, maybe, it's a little air out of a ball. If you could hit someone with a ball, at 60 yards away and hit them square in the chest with the ball, but you had to take a little bit of air out of that ball, is that cheating? Or are you a god among men as a quarterback? Peyton Manning, excellent quarterback. Maybe tied for best with Tom Brady. A little love to Tom Brady right there. And Peyton, of course. So make this all controversial. I like it, Emerson. So we'll have Emerson say what his team is. And then Will had a question earlier on, how do you find the p-value of an interaction? Well, it depends. The answer is it depends, because I can find the p-value for an interaction pretty quickly when the interaction is simple. It really depends here. Let's look at a interaction right here. Let's predict height. And I like to do simple stuff. With weight and I believe desired weight, this is the data set I know. We could do GPA. Desired weight and weight are highly correlated. Oops, I put a second tilde. It's going to destroy it. And I need to put a star. So if you notice, this is going to make my life easier right here. Okay, and there's my model. I just use M all the time. I overwrite my same model. If you want to use your models backwards, probably use different names. I just create things on the fly, and I have probably one of the most messiest R's that exist. Go through an autoregressive model. Yeah, we might touch a little bit upon that. So we might look at a little bit of time series modeling here. That's the GLS function, and make sure I have that on here. GLS. I might throw up some of the notes here too. So time series is at the very end, those very end bonuses, and we just kind of mention time series. So I'll mention those time series model in an autoregressive. Now do remember, Taylor, we will not have anything time series related on the test. There's only one bonus question on it on the take home. There's only one bonus question that is time series. Number 10 is not time series. I've gotten a lot of emails about it, and I know I know Riley's completed it. I'm trying to think who else. Who has done number 10, which deals with the trends, and they can say, yes, we definitely covered that in an assignment. That's been my big tip for number 10. Like, who can be like, yep, that's definitely in an assignment. Like, and if you look through your assignments in the notes, you'll definitely see it. Because I've had people be like, we didn't do this. And I'm like, no, it's there. It's there. You just might, it kind of, we just did it kind of, we talked about it in class a bit, and we did it one time on an assignment. There's just so many things we do. It's like, wait, we did that. So just want one person to be like, yep, Brown, we did that. Because I get a lot of emails like, we didn't do. Oh, you're free. That's free. Riley says assignment 8. Yep. Thank you. So Riley even said the specific assignment to help you guys out for number 10. I think it's fair enough to say, hey, go look at assignment 10 for a little bit of assignment 8 for that one for number 10. So it's definitely there. I've just literally had people be like, we did not do this. And I'm like, yes, we did. I promise you. It's also included in the time series. It's in the time series notes also on how to do that thing with time series. So now it's like, hey, here's how to do this topic you've already done with time series, which is number 11, which is also in the time series notes, and time series is a number 11 question. So that's why people get confused. They're like, wait, is this time series? No, this is just trends and data. The question on interactions, well, we can do an interaction here, and hey, there's the p-value of the interaction. I can also look at the p-value of the interaction with the drop 1 by doing drop 1, and wait a minute, where's my p-values? Well, I'm doing a linear model, so I have to do test equals f. For linear models, it's test equals f, and it gives me the p-value of the interaction, which is the same. Let's just view those two together. The p-value, and I will be posting this afterwards, if you notice here, this p-value right here is the same as this p-value right here, because it's the p-value for the interaction. And why is the p-value for the interaction the same as the other p-value for the interaction? Why in the world is that? Well, this interaction is just one estimate. It's just one estimate for our model. Hence, it takes up 1 degree of freedom. We don't talk that. You won't hear degrees of freedom on the test. But the degrees of freedom are the estimates needed in the model to create it. Well, what if I change this? What if I make it handedness? Well, handedness has with it 2 indicator variables, one reference, 2 indicators. And we can see that right here. That as indicator variables, handedness has with it left, right, and then it also has with it the interaction, weight with the indicator left, weight with the indicator right. So now when I run this right here, I get the p-value of the interaction. And once again, I said you can't average these two up, but it is, once again, if you notice, this is down here is definitely not an average of these two. But once again, generally when you see higher p-values, yes, can we go through the different tests for drop 1? Great, that's kind of what we're talking about now, Ken. That's a really good thing right here. Never mind, need to pay. Oh, there we go. So I'm just reading your mind, Ken, right there. So we'll make your mod 2 here. If anything crazy happens, you guys got the powers now. Okay. So this right here, the reason I'm using test equals f is that this is a quantitative, and we were just doing some stat tool 1 in my office earlier on, and we saw that all of a sudden when we change it, if you noticed, I have it up right here earlier. If you notice, all of a sudden here, when I run my model here, and kind of good notes, when I'm running it here, I'm predicting a categorical. So when I run it here, I use chi-square. If I try to use f, what's it going to say to me? Oh, it did it. Yeah, but it's wrong. That's not how we calculate. We calculate with the chi-squared. I didn't know it actually would do it, so ignore that. I might actually look into those differences. It calculates the AIC the same, but it doesn't use the f. Since it's categorical, we should be using the chi-squared. So the chi-squared method here. And maybe some stats nerds would fight over f and chi-squared. But with this one down here, this model I do not believe will run with chi-squared. I'll be shocked if it does. What'll it say? Ran. Give me the PI for it. But once again, I'll explain why. And if you notice, these are different ways of estimating it. if you go back to the ways we did stuff in Stat 201, the chi-squared test of independence is for categorical data. And with that in mind, that means the y is categorical. If you have categorical data, they're both categorical. And that's when we use the chi-squared test of independence. And this is height right here. So this is a quantitative. Now the F distribution, if you look at what an F distribution looks like, I can basically, the F distribution is the distribution of two T distributions. Works off of that. It's the ratio of two T distributions. It has 2 degrees of freedom. And I wonder if I can do random F. So you can do random uniform right here, and this will make random uniform numbers. So that's 355 random uniform numbers. Can I do random F distribution? That would be how many numbers, and this is the degrees of freedom. And you can. So let's turn this into a histogram. So this is random F numbers right here. And I believe if I make this a lot bigger, we might see something a little more normal. But this is the F distribution right here. It's the ratio of 2 T distributions. If I change this to random T, I need to bring this down right here. A T will look normal. And of course, if you see any differences from normal, it's just the bin widths. But the ratio of 2, which I wonder if I do this, if I can make... I've always been trying to figure out how to draw the F by hand, and I'm never good at drawing it by hand. I just know it's the ratio of 2 T's. Yay! Look at that! Oh, because if it's the ratio of 2 T's and they're both the same, the center of it's going to be 1. Whoa! Brian just taught himself something. Because I've always known theoretically it's the ratio of 2 T's. So you got your what's it called? Your numerator and denominator degrees of freedom, and it's the ratio of the 2 T's. So wait a minute. If I make this one 100, it's going to be centered at 0.5. It's not. Okay, I thought I learned something. Okay, enough of Brian learning. Oh, wait. Okay, I think I understand it more now. You don't need to know these things, but it's starting to make more sense in my mind, at least. And if I make this way low, we're going to see something crazy here. Okay, Brian doesn't need to know these things. I mean, he tries to teach himself. But if I've always wanted to be able to draw the F by hand and try to figure out the certain things, and that's what we have going on. But I want to make this clear. We're using the F because it's based on quantitative data. Theoretically, that's why. If you're like, why F? Why chi-squared? F is quantitative because T is quantitative. You remember me in Stat 1, I say Mr. T is mean. So Mr. T's brother is F. So F is the F ratio, which we talked about a lot. And we have going on right here the numerator and denominator degrees of freedom for these two right here. And you don't need to know this theoretically, but I just kind of wanted to delve into why F. F is for quantitative. Why chi-squared? Chi-squared is for categorical. And it looks like mechanically we can do things, but it might not be assumptionally correct. So that's the issue. It works, but assumptions are not met. So there's underlying assumptions when you perform a test. So if you were to use the wrong one, you'd use the wrong assumptions, and then your p-values are not reliable. Wrong assumptions, your p-values are not reliable. So we need to use the right assumptions and have the right reliability. So I won't delve into that theory, but once again, if you want the shorthand of everything Brian just went over right there, we want to use the F when it's quantitative Y. We want to use the chi-squared when it's categorical, which literally goes back to the chi-squared test of independence for categorical data, and goes back to regression where we assume the distribution has normality at for each given X over the interval of Y on that X. Okay, throw me those questions. We did a lot of really great review there. I think I've covered the one the person wanted in an email. I would like to... yeah, because we talked about number 10, I think. And so we got some... For number 7 on the take-home, would we break model hierarchy if we use the all possible message? You still wants to use it or use the step method? I can't remember exactly what that one says, Cooper, but follow it exactly. If it says pick the one with the 1 standard deviation rule or anything like that, pick that model. So be very clear. It might be one that says like pick the one with the 1 standard deviation rule. Don't worry about, but wait a minute, it does this. Be like, pretend there's no other things beyond that. And of course, I think that one uses train data. So when you, and here's a good bridge to a new topic right here. And let's make some train data right here. And so with train data right here, let's do it the classic way in the notes. If you're making train data, so this will help with the theory and it'll help with the take home. If we're going to make some train rows right here, what we're going to do is we are going to sample, and we're going to take a sample of, this is what we're taking a sample of. Let's take a sample of survey 10, or we're going to take a sample of 1 through survey 10. Lots of ways to do this. And I'm making mistakes in here. I want to show you what this code does as I do it step by step. This right here is the rows in survey 10. If everyone can agree on that. Oh yeah, we'll do that next. We can use that right here. Great job, Paige. We'll do that right here. This is just the rows. And then if I take a sample of it, it's going to randomize them. But then I want to go in here and I want to take like 70%. Why 70%? It all depends. This is a much deeper topic than we get into with predictive modeling and the amount we put in a holdout. It really depends on how much data you have. If I had 10,000 observations, I could make different holdouts. I could make 5 different holdouts of size 500. Being able to make a predictive modeling is like literally getting a job. Imagine being able to predict stock prices, or predicting if somebody will default on their loan, or predicting when someone will die, or if they will die this year, or like, this is like the whole idea of an actuarial services. It's like, if I got that right, figuring out all this costs and everything. This is predictive modeling. And so you need to know your model works, and we need to create a model from some data and test it on another set of data. So the second part right here is the size of it. If you look right here, I'm going to take size, the number of rows, and this is just a number. This part of the code is just a number, and then I'm going to take this many of these numbers. That's all it's doing. It's say, sample these numbers from here to here, and then take this size, and I'm just going to store it here into train rows, which is the 489 numbers I've selected, and it's just a random order. You can check what you made. It never hurts to ever look at it. I always ask students, I'm like, well, what does that look like? Yesterday we were looking at a model, and I was like, well, let's look at what's there. Let's look at what's in there, and something had been saved over it. So always take a look at it. It's just gets you better at coding, and always run your lines individually and create your code kind of organically. Like, don't write the whole thing, because it could have a problem. As you get better and better, you start to write it more at once. But I still make mistakes. I've made them today. And so here we go. We're going to store the train data, and we're going to take survey 10. I think I did the height, weight in class. Let's do something different. I'm also going to put before this, I'm going to put a set seed, and I'm going to run it this way. So if someone were to run this code afterwards, they'd get the same. We'll go with 320. And so if anyone runs this code here, they'll get the same results I got. This right here just appends the code. This semicolon, it runs 2 lines of code at once. It just ensures that if anyone creates this, they will also create the exact same. It controls the randomness. Set seed ensures that you get the same randomness procedure each time. It's still random. I didn't look at 320 and I'm like, haha, I want those results. It's just the random results. I'm going to get the same random results. It's a bingo card with numbers on it that I'm going to get the same every time. I can run this right here, check my train rows, and the last one is 613. And what are the odds? A random procedure, and I get 613 again. Whoa, but it's because of that. So let's continue on here, and let's take these train rows and put them in right here, and boom, put it in, and that's our train data. This comma is very important because we're dealing with a data frame. Survey 10 is a data frame, and let's go here. Let's change this to holdout, and now we need to make the switch that we have not the train rows. And you should look and you should say, okay, my train data set has 489, and my holdout data set has 210. Make sure. If you notice, those add up to 699. So let's look at the one standard deviation rule here. And we're also, I think there was another question. I think that was kind of it. Let's build a model. Let's build a model where we are going to predict. Let's predict something different. Let's predict GPA. It's probably gonna be a harder one to predict. GPA tilde dot. Now I'm using tilde dot because this uses the all possible model procedure in the build model, and so it's gonna search through everything here and tell us all the best models. And we're gonna put data equals, and data equals survey 10. Let's go here and run it. It should run. It says there's a lot of models. Sure, I know that, but you're fine, little MacBook Air. You got this. Here we go in 5, 4, 3, 2, 1, and we got it. Cool. What did it get mad about? Got mad about something, but it looks like it ran. And oh, I didn't store it into anything. Let me store it into something. Model, or let's just call it build model out. Okay, let's rerun it. It'll be like, hey, do you really want to run this? Say yes. And maybe I'm noticing when it said like, you may have to force quit R if this does not terminate. I don't know if Petrie had that in or what. We're getting a parse text fail. I haven't seen that. Unexpected end of input. Hey, but you know it ran. Looks like it got it. Let's look at the build model out here. Oh, it didn't run. Dun dun dun. What is it getting mad about? Well, I've been running this command for a long time. It looks like, oh, okay, 5,000 pointer. What did it get mad about? What's it angry about? What did it do? What error do we have? Why is nothing stored? 5,000 pointer. If you're rewatching the video, this is not a test code. Not wrong data. Not seed. It's in the output. It's in the output why it got mad. I see it. There needs to be an if statement in Dr. Petrie's code. There needs to be, nope, I'll make this. I will max you out on your extra credit. I'll put 999999999 for extra credit. You're going to beat Stewart, who had the record for extra credit. Ooh, no. Oh, Kenny, I'm throwing you 5,000 points. Kenny. Oh, Kenny, no. Brian made a mistake. Sorry, it's so easy. I'm sorry. Kenny, you're not, okay, everyone who said train, yeah, everyone who said train and Will and everyone, you get 5,000 points. That was a mega error on Brian's part. That's not why it crashed, but that was a big error on Brian's part. Sorry about that. Big error on Brian's part. And it still crashes, and I know why. And it has to deal with this. So, no, I'm just cracking up, Gudong, right there. Sorry. You guys are right. I need to use train because I'm building a predictive model. Maybe I wanted a descriptive model. Maybe I was just tricking you guys. I really wanted a descriptive model. Well, then I should do type equals descriptive, right? I really wanted a descriptive model, so I was using the full data set for my descriptive model. I will max you out if you tell me why this crashed, why it gave me the angry error message, and everything is available on the screen in the lower portion with the graphic and with the lower portion of the screen. Everything's there for you to tell me why this crashed, and you will get your full bonus of extra credit. One person gets it. I'm gonna let this go for about half a minute more. Not the build tree. Build tree is on the final. It's just bonus though. That's just one of the bonus questions. How to build partition models. Someone's gonna see it. I want you guys to get this. I want someone to get maxed out. When you see it, it'll be an O moment. I'm gonna give more hints here. It has to deal with this. It has to deal with that. And it's also in the output. Kenny, you got it. You're right. Kenny, what model is that then? So when it found the best model that with the one standard deviation rule, it had no variables. So the way Dr. Petrie coded this, because this is his function, I'll have to tell him, hey, there's an error in the build model function that if you get the what model, it'll crash, which maybe it should, because the answer is no model. The model that it picked for us with the one standard deviation rule was the what, and this is a good review of the one standard deviation rule. The reason it crashed is the model it picked with the one standard deviation rule, no one's saying in the chat, is the zero variable model, which is, Will got it, the naive model. Well, I'll throw you another 5,000 for that, and then Emerson, it picked the naive. So if you look at the way when it tried to write it, because this is what it tried to write, the function itself probably has like, take these variables and add them into this spot. So when it tried to write our model, it didn't have any variables to put in here with blank plus blank plus blank plus blank plus blank. So it couldn't do that. And so it just did GPA tilde, and then it did nothing. And probably we'd get this same exact error message if I went right here and ran this. And then it's giving me that, but it's bonking, and it's unexpected that, but it can't make the text. It's saying that it's basically GPA tilde. And so that's kind of the error we're getting right there. Because it got the naive, it crashed. And let's talk about the one standard deviation rule, then let's make a better model. Okay. So the one standard deviation rule states the following, that all models within one standard deviation are basically identical. All models within one standard deviation are basically identical. And the way this calculates it is the following. We take the best model, and then we go up one standard deviation of our uncertainty. So if you look, here's our best model. This one did the best because it has the lowest estimated generalization error. The estimated generalization error comes from the validation. That's key. The estimated generalization error comes from the validation. And the validation is the internal validation of our model by using the k-fold cross-validation process. Review that in the notes. So with this in mind right here, here's our best model, but it could be as bad as this. That's why this dotted line appears. So, and you look at it, no model goes below that. So that's why we're not going down to here, because there's no model that does as well as that. Our best model could be as bad as this, and this model here is in that range. So it's like your friend ran a mile in 6 minutes, you ran it in 6:05. That's within one standard deviation. So it's like, well, you're about the same. I mean, your friend beat you, but who's to say you couldn't beat your friend? I mean, at least with your interval, you might be better, or your friend might be worse than you. We do make it off of this one right here, so we didn't have conclusive evidence. Frankly, all these models are identical, and they're all pretty bad, because they all do just as good as the naive, or at least they're indistinguishable from the naive. Here's what the naive does, and actually its probability, or its ability, which is not a probability. Its ability, as in its typical miss, what we think it'll do on new data, is about that. And so it's a really bad model. Let's try to predict. Oh, we'll predict weight. Okay, we'll do the easy one. So I think we did height in class last time. Yeah, we did height. So height's probably going to be in this model because height's such a good predictor. And you notice it gives the formula. If you want to predict someone's weight, apparently the best variable to predict weight is desired weight. And if you notice what happens here, if you notice this really complicated formula right here, that's the formula for this one in the graphic right here. I mean, it's hard to see that. Maybe that's the 9 variable model. We'll find in a second. But the 9 variable model has similar performance. Just look at how high this goes, because that's the lowest RMSE we get. The 9 variable model has similar performance to the 1 variable model. I can tell it's 1 variable. That's easy enough to count. It's not 2. This is y tilde x. These are all the x's right here. And there are 8 x's. I started to look, I was like, I think that's 8. There's 8 variables in our best model. There's 1 variable here. And imagine if I said, I can predict your weight if you tell me 8 variables. That's a lot to tell. And I might be off by about 17 pounds. Or I can predict your weight if you tell me 1 variable, and I might be off by about 18. And if you look at here, of course, that's just an estimate of about how much we might be off with the validation if we use it on new data. So we can also see how this model does. And of course, the build model out stores this model. And I always wonder why you can't put this into, maybe today it'll work for me. But the build model out, it's showing the variables right there. That's the summary of it. So we need to go to the best model. Here it is right here. So there's the best model. And what's so weird to me, and I never get this, is you can't use this in the generalization error function because that is a model and it gets holdout equals. So see, it doesn't like that. It's never like that for some reason, but remember we can go up here and grab our formula, and the formula here is weight desired weight, and let's just go here, m, save into lm, and we go right here, and remember we need to make it on data train, and we make it on the train data. Brian even forgets every once in a while. And we go here to M, and it's getting mad at me. Oh, because I have the best model still on here. And there we go right there. Got it. And we can talk about this right here a little bit too. We talked about the 1 standard deviation rule. If you notice, the data our model was created from, it had a typical miss of 17.3. So the data the model was created from had a typical miss of 17.3. Where when we look right here, or no, sorry. Guys, I read the output wrong. The data, and I think this is just these decimal differences are just, if you look at right here, I think it's just the calculation, like either Dr. Petrie's carrying more decimals or they're carrying less, but it's just sort of rounding differences between it. So I've noticed small differences, nothing ever big, but it's just the way in which it's calculated. Maybe they use a more exact calculation, maybe he didn't, I don't know. And at the end, I just have my R carry out more decimals. So I don't know how many decimals his calculation is carrying through. You know what? Let's take a quick peek under that hood there and see exactly what's going on with the generalization error. Does he do any rounding? So if you look, it's all these RMSEs right here, and maybe somewhere in here. Oh, this is the if function right here. If it's categorical, he'll use the misclassification rate. And here's all the RMSEs right here, and maybe, just maybe, it's rounding somewhere. So I don't know. Maybe it's not carrying enough decimals. But with that said, let's go back to the question, take a look at it right here. So what we have right here are a few important things. We'll look at the miss. Oh, we did that on the holdout. Oh yeah, we'll do that for this problem too. We'll have to switch. So the reason this is not misclassification, Will, I want you to tell us in the chat, why is this not misclassification right now? Why are we not looking at a misclassification in the holdout? And the answer is actually in the code right here. If you look at all this right here, if this is equal to this, he's got a bunch of if statements. So why are we not using misclassification? You'll see maybe other if statements. You've got if statements right there. It's talking about what kind of model. Ooh, classification right there. So you can look at the whole thing. Man, this function, yeah, it's a pretty long function. So you are exactly right, Riley. It is a quantitative y, and quantitative y's are the typical miss we have because we're predicting a quantitative value. So we're looking at the RMSE of the holdout, which is the typical miss we make on new data, and we have the typical miss we made on the data it was created from. So now I'm going to ask Petrie maybe why he has small differences. It's only in the hundredths, but still, I don't like it when I see differences in output. So the typical miss we make when we predict on our data is 1813. The typical miss we thought the model would make is about 1813. And you know what's crazy? Is this model overfit or not overfit? Is this model overfit or not overfit, and why? Would RMSE be lower on train? That is correct. Emerson, you are right. Overfitting, and that's why I said, overfitting is when the holdout does way worse because the RMSE is lower on the holdout. It actually is performing better than we thought it would because we see here it performed this, 1813. This is the validation. We have the RMSE train, which is how it performed on the data it was created from. The RMSE validation, which is how we estimate it'll work on new data. And then we have the RMSE holdout, which is how it actually works on new data. And maybe it's because we got an outlier in our train data set. You know what? Of course I want to look at this, right? So I'm going to make right here, we've got our linear model, and let's just go here to the visualize. I bet you we got an outlier in our, just rewind that video. What did Brian say? I bet we got an outlier. And what's an outlier going to do? It's going to dramatically increase it right there. So we have an outlier right there going on in our data set. And if we were to look at the holdout, this is not, let me just do it the way, let's do it this way real quick. I'm going to go here to plot. I can't put a line through or it'll fit the line to the data. So we're not going to fit a line to it because that's not what we do theoretically. The line that we put in is from, if you look at that stream of points, yeah, you can see the difference right here. I need to get better at my ggplot skills, right? And I could quit. Yeah, look at that. This is why this is the original train data. And you notice the train data has this mega outlier right there that is going to dramatically increase our typical miss. Luckily, we're more robust to it now with RMSE instead of MAE. We don't cover MAE. And then right here, this data has a relationship. But if you notice, the difference is, don't these relationships look kind of similar? I know they're scaled a little bit differently, but if you look at them, you can kind of see the line that goes through this is the same line that goes through this. So definitely we have it. And that's why the typical miss on the holdout's a little bit smaller because the train data has this mega outlier dramatically increasing your typical miss. So that's why we see this right here. And I want to throw the harder theory questions. It's like, I just think of these things sometimes like, well, why is it doing so much better on the train? It's because something was dramatically bad inside of the train data. Why is it doing so much better on the holdout? So does everyone understand kind of why here that this model actually works better on the holdout? This model works better on the holdout because the typical miss on the holdout is actually lower than the typical miss on the train. So it performed better on new data. And is this model, is it practically useful? Maybe. I mean, we can predict someone's weight within about 17 pounds. Because if someone said, imagine that, okay, one person, you have to tell me in the chat, how much do you want to weigh? And let's do this. I'm going to write the function for it here. I'm going to write a function for this, and I'm going to write a function, one person. Let's say we're going to put in weight right here, and sure. And then we're just going to go here, and all we need to do is take and say return, and let's go here, weight, concatenate, weight plus 17, or we'll do 18, or minus, let's do minus, and then weight plus 18. Okay, so guess weight. No one said in the chat yet. Sure. So let's say guess weight, and how much do you want to weigh is the question. How much do you want to weigh? No one's responding in the chat to this yet. So how much do you want to weigh? And if you were to tell me how much you want to weigh, see if I said how much I want to weigh, I guess, I don't know, 175. So let's, Nate, do I want to weigh? I don't know. Maybe I want to weigh about 183. That's good right there. I want to weigh 183, and right now I weigh about 191. Both intervals contain me. So Riley, if you want to weigh about 120, then It'll guess your actual weight right there because you can look at how much we typically miss. So that's all this function is doing right here is saying, well, we typically miss using what people, and remember, this is the typical miss. It doesn't mean we will miss by this, but usually we're going to miss by about this much. So, a lot of times if we use this here, someone's weight would be contained in this interval, but it's also like a 68% confidence interval for like one individual. And actually, speaking of, we could do those things right here. We could use the predict function. We didn't use this a lot at the end of class. I think I just have it here as my model, and I could predict, and you could just look at all the predictions right here. And we could go here to level equals 0.95, and we can make predictions. So did that do all the intervals? Is it interval? I always forget let's do, interval equals confidence. So it's doing, we could give it the holdout data. Sure, let's do that. New data equals holdout. So now it's predicting on the holdout. Is it not? Wait a minute. Why is my model getting mad at me? You guys can yell at me. Predict, model, and new data equals holdout. The holdout. Oh, these are the row numbers. I was like, why does it have 698? Those are just the row numbers. And interval, so level. It should be level. There's so much syntax to remember. I'll see if you guys have another question here in a moment. And what is going wrong with my predict today, guys? Why does Brian forget how to use a function randomly? Predict, model predictions. So require utilities. Of course it looks all weird right here. So ask those questions in the chat if you got them. New data, interval equals, level equals 0.95. It is level. And interval equals, I think I just need interval equals now. And that's confidence. There we go. So, it is interval. Nice job, Cooper. Yeah, it is. And so you can see somebody's predicted weight right here. And if we want to go for an individual, it would be a prediction interval. And if you look at the widths of these intervals, then I'm guessing since these are 95% confidence rolls, 2 times 18 is 36. Look at this. Since this is a 95% confidence roll, 2 times 18 is 36. The difference between these is basically 36. So you can see where a lot of these numbers come from with 95% confidence rolls. 18 times 2 is 36. And if I were to change my formula here to a 95% confidence roll, or basically like it, if you see right here, we have someone who weighs 160. And if I go to guess weight 160, and I'm basically making a 95% confidence roll, we'd have the following, 124 to 196. And if you go to the first individual right here, it's basically 124 to 196. So once again, my thing is basically doing what this is doing right here, creating 95% confidence rolls. It's doing it more exact. Once again, I put 160 in, and then it does that, just kind of understanding theoretically what's going on right here. So it's pretty much doing the same thing, just more exactly. Questions, ask them in here. I think we wanted to see how to do the misclassification rate on a holdout, and we need to make a different model right here. So let's change the build model. It's a pretty flexible function. And the build model here, let's just grab it. And let's go down and run this right here. Let's change it to predict gender. And let's do it on the trained data. Sure, I'm good with running it. It's getting mad again. This one right here, it's saying it must be GLM. And let me see here how Dr. Petrie made it do the predict on gender. So I rarely use build. The really great package for this, I wish I could use train right now. The really great package for this is train. I so rarely use build model to predict on gender. We could actually make a model here pretty quickly on that. And so when we have here type equals predicted, prompt, repeats, and we should be able to get it to work on a GLM. So form, and if we see right here, we have predicting salary and predicting wine, and there's quality, cool. So if you notice here, this is quality, seed, holdout. Well, he's saying this should run. He's saying not run. Dr. Petrie, no! Let's grab this right here. He says do not run it, or does it not run? Predicting model for wine takes a while. So he's saying don't run it. Let's grab you can always grab these examples right here and run them. Should run. He says it runs. Do not run it. Too bad. I'm running it. So we've got here the wine data set. We're going to set the seed to 2010. We're going to put replace equals true. Cool. We make our data. And then let's run it. Well, it is running. I didn't think there was anything extra. So I think it got mad at me. I don't know why it got mad at that one. You hit errors once in a while. Let's see if this runs, and let's look at our misclassification for the quality of wines. We'll give this a moment or two longer. The wine data set just has the quality of wine high or low. And maybe this will run. Maybe it won't run. I should have limited the data frame. Oh, it ran. Look at that. And I really like this second graphic you get. I haven't seen that one in a while there. Because what's super cool about this is the following. Is it's actually using the holdout, and it's showing you it usually does a little bit worse on the holdout. And I think actually, oh yeah, because he put holdout equals holdout. So you get the second graphic. So actually, you know what we can do right here? We never see this. We never see all the cool things it can do. You could do this right here, and when you run this, oh, what's it getting mad at me about? Oh, my train data is wrong now. Let's remake our train data. Always fun times, right? My train data is a different type of train data right here. And so let's go back and predict height. And just so we can see this again right here, maybe I shouldn't have redone my model. But you get this cool graphic right here on the right that shows you how it's actually performing on the holdout when you do holdout equals holdout. And wow, yeah, because remember, our graphic had that outlier, so we actually see that we'd predict it would do worse, and it actually does better in the holdout. So that's what's going on with that graphic there. So I'm going to remove the holdout equals holdout for now. Reason being is I just don't want you to see that extra graphic because it won't be included on the test. I would hate, what's it getting mad at me about? Oh, got to redo my holdout. And so, because I'm changing what my trains and holdouts are. So there we go. Okay, so very important stuff right here. We are now predicting a categorical Y, and I don't know why it didn't like that one time when I did it, because I swear that's what I'm supposed to put in. Might have just had some sort of impossibility in the data and ran into some sort of, oh, can't compute this. And sometimes codes do that. It's like, you have things that can't compute. And so with this in mind right here, we're predicting the quality of a wine from the training data. It's only taking about another 10 seconds, and we're going to get graphics similar to this. Now let's look at what's going on with this graphic. We have the number of variables in the model. And once again, we can review the one standard deviation rule, which states, the one standard deviation rule says go to your what model? Your model that is the best. Here's our best model. This model's within one standard deviation of it. This model here is the naive model. Now this is the estimated generalization error, and this is a misclassification rate. Why am I dealing with misclassification rate? Why am I predicting with misclassification rate, and what type of models am I building? These are all very important things to know like this. Like, oh, I'm dealing with misclassification rate. I'm definitely dealing with this kind of model, this kind of data. So you should know those things pretty quickly. So we'll see if people say anything. Chat's been quiet for a little bit here. No more silence. So we are dealing with misclassification rate because this is a blank variable, categorical Y. Boom. Misclassification rate with categorical Y, logistic regression, all that good jazz going on here in the background. If you notice, it did say non-Gaussian, which means not normal data. So it's dealing with non-Gaussian type of family right here, which literally once again is non-normal data. So with this right here, let's take a look. It says our best model is the following. Now, luckily for us, this model can be easily made. So let's grab the data right here. Let's go here and just make a model, and we're going to go GLM, drop that formula in. This model violates model hierarchy because it has the interaction between these two. It has the interaction between these two, and it has alcohol. If you notice, one thing to point out here is this is variable 1. Variable 1 is an interaction. Variable 2 is an interaction, and variable 3 is this. That's why it has 3 variables. Yes, GLM. Yes, that is why. I think Riley got it right there. You are correct, Riley. And data equals train. Don't forget that data equals train. And then also family equals, I don't know why did I type in the wrong function? Oh, that's why it's not auto-completing. There we go. I noticed it wasn't auto-completing. I was like, what was wrong? Because now it should auto-complete. Cool. You can type family equals binomial here. Don't let it autocomplete for you for once in your life. And create that model. What is it getting mad at me about? Quality. Data equals. Family equals. Oh. Typos. What is it saying? Volatile is not found? Did I remake my train data? Let me look at my train data. It's saying volatile is not found. Does volatile have a space? Did I misspell it? It should find volatile. It's saying it's not finding a certain... Oh, I've seen this. That's not an interaction. Damn you, Dr. Petrie. There we go. Sorry, there's always something weird or wrong with code. It's that for some reason when it takes that period, all these little things I need to tell him. If you notice, those looked like they were interactions that violated model hierarchy, but when it runs into that dot right here, it actually turns it into a colon. Isn't that weird, Will? Like, I thought I had it right, and I was like, oh, volatile's not in here. Oh, it's volatile acidity. So, weirdness, I won't quiz you guys on this, but that's just when you have to be like, why is my code not working? So we always try to figure out, Will, 5,000 points. You saw it like when I did. And sorry, I've been reviewing all day and writing tests all day, so sometimes my brain breaks a little bit. Here we are with our summary of our model. Let's try to interpret the coefficient of residual sugar. Try to interpret that coefficient of residual sugar, and I'll give you a little bit of help right here. Interpret the coefficient of residual sugar. Try to interpret that coefficient of residual sugar. You better believe there will be questions on the test like this. And there... That's not what I wanted. Because you need this right here. That's what I wanted. Okay. I'm like, why am I doing the levels of residual sugar? I was just saying it a whole bunch. So interpret the coefficient of residual sugar. Interpret the coefficient of residual sugar. So I'm thinking about it in my head right now. Write it in that chat. Interpret the coefficient of residual sugar. So got it. It's gonna sound weird. You can flip it. When you write the interpretation, remember, pause the video if you're reviewing this right now. Be able to write the interpretation, and I've given a huge hint right here. But it's gonna sound weird when you say it. So, and is this individuals? I'm predicting what here? Don't say individuals. Watch out. A lot of people say individuals and stuff like this. I'm like, no, not everything is individuals. Not everything is individuals. I've written a lot of things, and I think I did this one time on a test, and everyone's like, 2 individuals, and I'm like, not quite individuals anymore. So let's see. I want to see that answer in the chat for another 5,000 points. These are 2 basically products. These products are wine, so I would accept that on test. 2 otherwise identical products, and otherwise identical because it's multiple regression. 2 otherwise identical wines that differ in residual sugar by 1 are expected to differ in quality, where the more sugary one is expected to have lower quality. Correct. So I would say 2 otherwise identical wines that differ in residual sugar by 1. The one with more sugar is more likely to be low quality. So it's... Ooh, careful. No. I think we got to reverse here, Riley. Is expected to have lower quality. Nope, Riley. So here, I'm gonna point it out. Don't worry, it was tripping me up too, but I think there's a error, and I'm gonna show it by making the model a little bit easier, and this will help out in viewing it. So let's review. It's very easy to get tripped up on these interpretations. Don't worry, that was only a small error, but let's view this right here. So what we see right here, and actually, let me make the model actually just from residual sugar. I'm just going to take and use only residual sugar. If the coefficient stays the same, which you'll notice the coefficient is negative. Ooh, it's positive? Ah, yes, because coefficients can change. Let's put alcohol in here. Since the coefficient was negative in the model we saw previously, I want to show you what that looks like. Remember, I'm going to do a negative coefficient because alcohol is always good, right? I hope, at least for this model. So if the coefficient is negative, which we do see, look at that crazy strong coefficient right there. So we see a negative coefficient. And now just think, 2 wines that differ in their amount of alcohol by 1 unit, but are otherwise identical. The wine with more alcohol is less likely to be... So this one is less likely to be lower quality. And if you go back to our output right here, the coefficient of residual sugar is what? The coefficient of residual sugar is negative. So the coefficient of residual sugar is negative like this. Now, this is not our model. I'm just using it to talk about the example. The coefficient of residual sugar is negative, which means it decreases the probability of the level of interest, which is why I showed this, because the one that is last is the level of interest. That's why low appears over here. Low is the level of interest because it appears last. And so the probability of the level of interest decreases as residual sugar goes up. So 2 wines that are otherwise identical but differ in residual sugar by 1, the wine with more residual sugar is less likely to be low quality. I know this is alcohol, but it still has a negative coefficient, and this hopefully shows the topic. Of course, if you notice here, alcohol is even more significant in this model and also by the simple model. But we're talking about the multiple model here, but I just wanted to show how a negative coefficient is sigmoidal down, which decreases the probability of the level of interest. Does that make sense? And that's why I said it's kind of confusing wording, because you're saying it's less likely to be low quality, i.e. more likely to be high quality. Less likely low, more likely high. Does that make sense, Riley and everyone else? This can be tricky. It's interpreting the coefficient of a quantitative variable in a multiple logistic regression. That's a tricky one. Definitely doing the outputs and practicing. I hope you guys kind of followed this example right here because it can get tricky. Oh, I get it. If zero quality is neutral and positive is indicative of bad quality, then decreasing bad quality means it's more likely to be high quality. Yeah, that's right. So what it is, this equation right here, as the equation goes towards zero, then it's less likely to be level of interest. And if the equation solves positive, like if we had a wine with no alcohol, oh, think about this. Imagine I come to a party and I bring a wine that has no acid in it, sure, no sugar in it, sure, and no alcohol. Does that sound like a good wine that you really want at your wine lover's party? It has no acid, no sugar, no alcohol. And this isn't acid, it's volatile acid that we use to make wines. And probably right here, when I tell you it has no alcohol and we're at a wine party, you'd probably tell me, Brian, that sounds like a low quality wine. And since this solves out it's basically water. There you go. Like, well, unless you're Jesus then. So, yeah, you'd be like, man, it's some awesome wine. Which apparently they said he turned it into the best wine. That's the story behind it. So, right here, we would say that that's not good quality wine. It's low quality. If you look, it'd be all the way down here. It'd be at the zeros. So, also, we can use this to solve. Imagine, let's do this type of question here. Well, we also asked about the misclassification rate of this model. So let me show you the misclassification. The misclassification on the holdout, we need to go here to generalize error, and we can view the misclassification of the holdout on our model by running the following. And to get the misclassification on the holdout, we just see where it gets it wrong. So it gets 134 wrong, and it gets 118 wrong. So that is the misclassification on the holdout. We would just add these two together right here, and then you notice it's this, which actually, when you look at this, it actually does better or worse. Ooh, yeah, so theoretically, we want RMSE and misclassification to be lower. RMSE is typical miss on when we make predictions, and misclassification is the amount we get wrong. And this one actually does better. It does better on the holdout again. But these wines right here, it depends. It says these wines were high and they're actually low. It says these wines were low and they're actually high. So you can kind of look and be like, where does it get the certain ones wrong? Like, where do we make our misses? That can be very important to a lot of analysis. Cost-benefit analysis would be performed on this to figure out where are you missing opportunities, because here's a wine we did not buy because we thought it was low quality, but it was actually high. Here's a wine we bought. So this is sunk cost, basically, like wasted money. Here's a wine we thought was high and it was actually low quality. There's all this stuff about wine. We were talking about it in my office one day about, like, how does someone even know a wine's high quality? I really would love to see the testing on that. I don't know. I just want to see, like, can people actually tell? One big thing I wanted to do right here. Oh, yes, let's use our model. I wanted to do this right here. Let's go back to our model we've created. Where's my model at? Surely I got a summary M in here. There's a summary M. Here, okay, try this hard question right here. Okay, be careful. Grab that pen and paper. Pause the video if you're watching. I want you, a wine has 10 for all of these values. Oh, no. Don't do that. A wine has 1 for volatile acid, and it has 10 for everything else. So it has 10 for residual sugar and 10 for alcohol, 10% alcohol, and 1 for volatile acid. The question would be too easy if it had 10 for volatile acid. If you know how to solve this, you could easily tell me what kind of quality wine it is. And just think the wine is full of acid. That should tell you, or way acidic. Like, way too acidic. And you say, Brian, how do you know that's way too acidic? Well, I bet you I could look at my summary of that variable, and it's going to be nowhere near 10. I'm guessing, for volatile acid, yeah, it's nowhere near 10. 1 is near the top. Cool. And I could explain how I knew, but let's focus on the question. It's going to have 1 for volatile acid and 10 for, and I think we need to interpret the interaction next, but it has 10 for the other ones. Go ahead and solve for the probability the wine is low quality. Tricky question. Lots of people get this wrong, and it shows you understand how to do different types of models. So go ahead and solve for the probability the wine is low quality. I am going to max out another person on extra credit if they get this. If you notice where Brian gives huge extra credit, well, the last one was a theory one that I just really wanted you guys to figure out, but this one, I see so many people get this wrong because it's kind of like we learn how to do something, then we forget there's another way of doing it. So what would be right here? What is going to be the probability this wine? And if you wanted to, I bet you. So I'm going to write something right here. And I'm going to start writing the code. You guys solve this. I want you to solve out that the wine with volatile acid 1, residual sugar 10, residual sugar alcohol, or alcohol 10, I want the probability it's low quality. So I'm going to start writing something right here, and it should work. I'm going to cross my fingers. Okay. Why am I down there? I want to go up here. There we go. I'm finally up here. I swear, I was up here, and then I wasn't. So be solving it while I write my code to solve it. So I'm going to solve it with code to find the answer. Cool. Volatile acidity. You know what? Why write when you can copy paste? Then you don't make any typos. Are you trolling me? I think when I do multiple screens, I have problems every once in a while. Let me pull this a little bit down further. Cool. I don't know if that's the issue. There we go. And you guys should be solving it. This is a tricky, tricky question. I see a lot of people make mistakes on. So that's equal to 10. And I'm not using a concatenate vector here because I don't have to. And I have no idea why. You click up there, and then it doesn't show up. Oh, I want someone to get this answer because I will see everyone missing this on the test. I'm halfway just giving away a test question here to be like, hey, know how to do this and know when to do this. So, so I'm going to do right here. I don't want to show the answer yet. I'm going to max someone out on extra credit. You have to get it correct. I'm going to try to solve it in my head. I know what the answer should look like, but to solve this, I'm going to wait at least another minute. You should be solving this right now with a sheet of paper because I see 80, 90% of people sometimes miss this question. And then I highlight it and I'm like, don't miss this. And just think, you should understand what's going to go wrong with people when they solve this. They're going to totally forget about something. Let's see, we're going to keep the chat going. I want you guys to pause on this. This is mega review. If I solve everything, a lot of times people will be like, oh, it's so easy. That's how we do it. But then they forget. You need to know how to do it. You have to be like, wait, for this, we do this. It's very important right here. So, new data. New data doesn't appear. I hate that about this function. Will, no, you fell for the trap. Well, you know what, Will? You know how I say answers count? If no one else gives the right answer in 1 minute, you get it. You know what, Will? I'm just giving you the max extra credit anyways. I appreciate it. No one was answering. You came in here. You gave an answer. You gave it a shot. You maxed out on extra. You tell somebody, I maxed out my extra credit just by trying. That's what matters. So thank you, Will. You got it. So I'm giving it to Will. And I'm putting 30-second cap on this for anyone else to figure it out. And then we'll explain why. And hopefully my code works. We'll hope my code works. And here's the thing also. You could type the code I wrote. You can write your code, steal my code right now, and be like, just be like typing it all up. Get it in there. Figure it out. We got like 10 more seconds. You better start writing that answer. You can max out your credit. And so I'll throw you 1,000 for that, Riley. Riley, you're right. But Riley, do you have the number? Riley, I'm going to give you like 20 more seconds. Do you have the number? I want the number. I want the probability. I want the probability. I want specifically the probability. And Riley, you're on the right track. You're on the right track. So we only have like 20 more seconds. We'll see if Riley can get the probability. And to max out, I think it's just some crazy typing and everything going on right here. We got like, you see this, there's a lag, so if I start counting down, you'll hear the countdown after I say it. So we're gonna go ahead. 3, 2, 1. Wait a minute. Oh no. Okay, no. You have to change this. Damn you, predict function. Wait. Let me explain what you need to do with this now. Let me grab this. I think there's a changing to it. I know, Will. Will, you got what I got. You're like, hey, Brian, that got it, right? Watch this. EXP raised to the this over 1 plus EXP raised to this. There's the answer right there. And so this right here, ooh, is that what it's going to be? Let me make sure. We get a positive number. Is it supposed to be positive? Did I type everything incorrectly? Volatile acid, residual sugar 10, and oh, because the intercept. Oh my god, I totally forgot about the intercept. Yeah, it is positive. If you multiply, and that's probably what you did, Will, but I want to point out what's going on right here. Is this model right here is a what model? So, and then you have to notice, what did I do? This is a what model. I'm predicting, look at your model over here, it's a what model. These are key things people forget. Let me put in parentheses. So, no, Kenny, no F for me. Pay respect. No, no. But with this right here, we have E raised to the regression equation over 1 plus E raised to the regression equation. Oh man, I gotta pay my respects too, you know. There we go. With this in mind right here, we got E raised to the regression over 1 plus E raised to the regression. So if you just solve it flat out, you will get 8.69. But what you have to do is you have to take what you get from the regression equation and then plug it into this. This is what it looks like mathematically when you're solving it. When you solve the regression equation, you do get 8.69. That is not the answer. The answer is that you have to get a probability by doing E raised to the over 1 plus E raised to. And of course, I forgot the regression equation doesn't know. And I think, let me see right here. The regression equation, this right here, does have a way of doing it. I so rarely use it because I solve it by hand. But there is an argument in here, I swear, for the predict to use it on GLM. And let's go to model predictions. And is this the A rules? I have too many packages loaded up. Model predictions, and it maybe has it here for GLM. There's predict GLM. Aha. Aha. So predict GLM. Oh, look, it's still doing that. We should see an example down here, but we can use that number. And then is it factor equals true levels? There's an argument we need to change inside of it. And, you know, every once in a while on the fly, you're like, no, wrong thing is termed to spit. Type. Here it is. Here it is right here. Type. Which type is it? It's not type response. You can use, let me change this. Type, what are the types for the predict? Type equals response. There we go. That's it. I couldn't remember. It does have that. And if you notice, this is the same thing I'm getting out of this formula right here. Type equals response. And you have to, we didn't really use the predict function much for that, but you can solve it. It needs to know the type is a response. And then all it does is it switches what you are doing to take your answer from the regression to do E raised to the over 1 plus E raised to the. This is the mistake I see a lot of people make. It's so easy to make, and it's easy to make with code. If you're like, wait a minute, because all you do is you solve the regression equation as Will did. Great job, Will. And then you take that number and you plug it into here, and then you do 1 over 1 plus E raised to the. So we do this right here, and that's the answer. And that's all it's doing in the predict function right there when you do type equals response. As it says, the default is for linear predictions. Do you see this right here? The default is linear. The alternative is response, and that is for a response variable, which is binomial. If you notice, it mentions binomial here. If you notice, when we built our model, we said in our model that our data was, where's our GLM? Our family is binomial. So if you notice, this is right here, and that's why we're doing it right there. So if you notice, so yeah, great job, Will. Great job, Kenny, too. And it's really easy to make mistakes with code, because sometimes something can run. You're like, hey, I got it. And you're like, no, that's not it. But I want to point something out. I'm not trying to pat myself on the back here, but I knew the answer was wrong because I knew it should be a probability. So that's something you should clue in on your head, too, if you solve this. And it's all right. I knew this would be a tough question, and even I made a little mistake here. But when I saw that, I was like, that's not the answer. And when Will put in the chat, and great job, Will, I was also like, that's not the answer because that's not a probability between 0 and 1. Because I know we're predicting the quality of wine, so I know I need to put inside of here a probability. So that's the key to it. It's like, okay, I'm predicting the quality of wine, which is either high or low, which is a logistic model. The numbers I can get are only between 0 and 1. And so you know you've done something incorrect. I also know if I increase the sugar of the wine, or let's increase the alcohol. Let's just get 100% alcohol wine. Which we'll just say that's 100% right there. 100% alcohol wine, and now let's predict. And if I had 100% alcohol, basically moonshine, you better believe that that's going to be some good wine. And you say, how do you know this is good wine, Brian? This is the probability of it being low quality, and that wine is amazing. And this is the simple model, but it kind of shows that the probability here is basically 0, that it's low quality, and it's extremely good. And let's just take out that acid out of the wine. We're just going to go here and just take some acid out of the wine and just use it to predict nowance. And I think this is the lowest probability it'll give. After this, it just doesn't return anything lower. I've got my round. I've set my global options. What other questions do you guys and gals have? So, a lot of F's in the chat. What other questions do you have? I think what else to cover. Let's look at this. We're almost done. We're almost done with tests and everything. Well, Thursday. We'll be done on Thursday. Let's go grab one of our earlier models. Let's see here. We'll grab a model here. And something we did a long time ago that, you remember, anything not on the last test could be on this test. Did I misspell influence? There's my influence plot. So my influence plot, whoa, what's going on here? How similar to the structure of last year's exam versus this year's exam? Maddie, maybe. I mean, go for a spot. I don't control it. All the people in the building control it. Try, Maddie. Hopefully I'll see you there. Be good to see you in class again. So how similar to structure versus this year's and last year's? I've been writing my exams, so kind of similar. I hope you guys join. I'm glad you guys, if you had fun and you learned. I mean, that's what I want. 2 things. Have fun and learn in class. I mean, I like class to be enjoyable, so that's what I hope I offer to you guys, and I hope I educate you. That's my 2 goals. With this right here, this point right here has extremely large leverage. It also has barely enough deleted residual. A deleted residual is a topic we talked about a long time ago. A deleted residual is found by removing the point's influence and then calculating its distance, its residual, its distance from the line, without its influence. Leverage is how extreme something is in its combination of x's. Leverage is how extreme something is in its combination of x's. So actually, if I were to find these points right here, I could take a look at these individuals and, well, we're just looking at their weight and their GPA. So let me go here, and I want to look at these individuals, and they're extreme in their values of weight and GPA. So we need to go, and we need to grab survey 10, and we need to go here and grab these rows. So I'm going to have to put some commas between these. And then they're extreme in their combinations, apparently. If you notice, these are the rows I want, and watch out, I need to put my comma here. And then I'm going to do something. I always try to learn how to code a little bit better. I'm going to put right here, concatenate. I'm going to try to grab these columns by their names. Because I believe since it's, a vector, a named vector, we can just grab it by its name. And we're going to hope that it gives me this info. And it does! Wow, I think I found my extreme person. Well, I hovered over them. Which one of these do you think has the most extreme kind of combinations? Which one? Which row number do you think is this crazy, 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 crazy amount? That crazy, crazy, crazy one that's off the rails is probably, and then I'll answer Kenny's question next. It looks like this is probably this individual here. If you notice, they have a 0 GPA and they're very, very light. What we could do is we could construct this same model, and we could go here and the other 560. We could remove this individual out and put it in, just do everything but them. And yeah, look at that. Found that person. And I want to point out again, how did I know it was that person? Because I know what leverage is. I know leverage is the most extreme. The more extreme you have in your combinations, then this is the most extreme. Like a 0 GPA, really? 0 GPA and also 95 pounds. That's an extreme combination, and so they were the most extreme. They were the furthest away in the bivariate sense. So when I removed that person, you see that point go away. That's literally that point with that crazy amount of leverage. You see the graphic kind of move over. And it also readjusts the model, so points kind of shift a little bit. So Kenny asks, what's the best material to look over before the final? Really what I try to do is I try to mimic a lot of your assignments. If you think about how I've been asking you, that's kind of always my goal. So the assignments I want, if you're able to do the assignments on your own, you're able to do well, and it's tough. It's, you know, it's tough sometimes. Like, think about how much of this can I do on the fly? You know, maybe if you've interpreted something once, you've done it, but think, can I interpret it again? Can I interpret, you know, a quantitative variable in a logistic model? Can I interpret a categorical variable in a logistic model? Can I interpret a quantitative variable in a multiple linear model? Can I interpret a categorical variable in a multiple linear model? Do I know what an not identifier? Everyone, you guys have got me saying that this semester. I probably said it once and now everyone says it. Like, it's probably my fault. But can I interpret an indicator versus a reference level? Do I know what the level of interest is? Like, these are key terms right here to understand. And knowing like the graphics and what they mean. Remember last time I hit you guys with this output, we tossed that question. I'm not going to be like, hey, interpret what every value is here in this output. But I always kind of say in the class, like, know what everything is in an output. Know like what the R squared adjusted is. R squared adjusted is our R squared adjusted for how many variables are in the model. Know what model hierarchy is. You can tell that this model obeys model hierarchy because it has weight and GPA in it. We could do a polynomial trend here. Let's just look at a polynomial trend. So, and I think we still haven't mentioned the interaction question, I think, because that was asked earlier on. Let's do a polynomial trend on that. There we go. So that now did a polynomial trend, assignment 8, and now the output's too big for the screen. But now we have a polynomial trend for our data, and there's the polynomial trends. And the polynomial trends are not significant, and you notice, oh, because we got a polynomial interaction. Oh my gosh. And if we want to pull these out to look at the significance of an interaction, and I think it'll only pull the polynomial interaction, we once again can go here, test equals, and we're doing F because we're predicting height, and now we get and it's only pulling out the one that would not violate model hierarchy, and this right here. And so it actually pulled out the full interaction on the third right there, and craziness. And actually, what does this do? Wow, that's crazy. This model actually violates model. No, it doesn't violate model hierarchy because it has polynomial trend linear interaction, all that good stuff. Pretty similar structure. Expect a lot of interpretation, Emerson. Expect a lot of interpretation. There's multiple choice. I'd say it's a pretty similar structure to the midterm, but with a lot of interpretation. Especially the things you're asked to do on assignments. When I say like interpret the coefficient, make predictions, I would say I've done 40 to 50% of the test right here, right today. Which I mean, I can't do the whole test, or I'd be like, hey, just watch this one video and you can ace the test. And I mean, how could I mean, it's kind of my nicety of being like, hey, there's some stuff I've done today that directly relates to you doing the test. Like, there's some stuff that directly relates. And remember, you can still send me those questions if you want, and I might use them. Maybe I'll augment them a little bit. But, I like if you guys are like, hey, you said this a lot in class. So I might not directly take your question, or I might directly take it. I've said that before. But if you were to send me 20 questions, I wouldn't. But, I like you guys coming up with questions. I like you challenging yourself. You can also send those questions to your friends in group meets and stuff like that. Feel free to share them. If you're like, hey, I sent Brian these questions. They might be good or bad questions. Probably, if you're understanding the material, you might come up with some good questions to quiz yourself. Like, you can look at this model right here and say, does it violate model hierarchy? And the answer is no, because, and you could say why, it's because it goes to the third order polynomial for weight, and it includes the second and first, so it doesn't violate model hierarchy. I mean, it's a quick and easy, like, does the model violate model hierarchy? No, because it includes up to the third order polynomial, and also includes the second and first order polynomial in the model. So that's good right there. Is R squared adjusted bad right here? No, because R squared adjusted, so weight actually came out significant with the second order polynomial. And was it the third? The third was not significant. But the R squared adjusted is not bad because it's very close to our r squared. And you could divide them. You could just take the number here on the test and be like, okay, the r squared adjusted is this much of our r squared, and the r squared adjusted is the r squared with a penalty term. So it's pretty much as large as our r squared. It's 99, but it's always going to be smaller, and that's got it. So knowing kind of what the output means, I always stress that. It's like, know the output, know how to interpret it. We don't interpret polynomial trends. To interpret an interaction, let's do an interaction on a categorical right here. So I'm just going to switch this up. We might end with this, but you guys can tell me if you have more questions. Okay, so we'll put that, whoever that was, we'll put him back in here. Cool. Poly weight. I don't want poly weight, I just want weight. Okay, cool. And now we go here. Okay. So I am not going to look at the plot, and I'm going to interpret the interaction. So when I look at this right here, I see weight and I see gender male. And be careful, I could interpret multiple interactions for all of these, but look at how interactions are interpreted. So let's see here. The impact of weight on somebody's height depends on gender male. So let's read it again. The impact of x1 on y depends on x2. If you notice how I'm doing this, x1's impact on y depends on x2. So let's think about this. The impact of somebody's weight on height depends on gender male. So gender male is an indicator variable. This is an interaction interpretation. So for individuals who are male, because if I turn this to a 1, it's going to add this to gender weight. Or it's going to add this to weight, excuse me. If I turn gender male to 1, the coefficient of weight increases by this amount. So what I would say is weight, the relationship weight has with height depends on somebody's gender. If somebody is male, there is a stronger relationship. And let's view it visually. And the answer is, and it's so hard to see the difference. No, if you notice, I think it's not statistically significant. It's not. And it's very hard to see this difference. But the male line should be more sloped. Let me throw GPA in here and see if we can get a better, more sloped line. Oh, now it's negative. So the male line is going to be... Oh, this is going to be interesting. This is not the plot on the side. Okay. So now, actually, males are going to have a negative slope. Because if you look here, the coefficient of GPA is positive, and that's for females. So actually, we got an interaction here. It's actually not statistically significant. It's just because this isn't statistically significant either. But females are going to have a slightly positive line, and males are going to have a very strong negative line. And we see that right here, that the male... Let me change the loc on this picture so it goes away. Let me go to loc equals middle. Is it middle? Loc equals... You can do middle. Sure, why not? Oh, no, it's not there. Let's go to... What's the loc? I swear it's middle. Is it mid? Loc equals mid? Oh, let's cheat. Let's do it this way. Loc equals x comma y. 0 comma 68. 0 comma 68. Will this work? I like that. Let me go loc equals 68. Okay, cool. That's good. That's where I wanted it. You can enter the location as a numeric, and it'll put it in there. Okay, remember I said males has a negative line. Let's put the output on the screen and take a look at how I knew this. Okay, so how did I interpret this interaction without even seeing it? That's the key. I know right here that GPA is for females, as in we don't have the indicator turned on. Can you write the line for females? The line for females is predicted height of females equals 64.45 plus 0.12 times GPA. And we did this in a previous assignment. But then we see to interpret the interaction, because that's just for females. And if you notice, females has a positive coefficient, this line goes up. But then to interpret the interaction, we see here that the relationship that GPA has with height depends on somebody's gender. Because when somebody is male, we decrease the coefficient of GPA by this, and thus it actually becomes negative. The slope of this line is 0.38. If you see here, if I go up about 3, it goes down by about 1-ish because it's 0.38. So if I go by 3, there's 3. And so apparently that should be about 1. Am I doing my math wrong today? Oh, it's 0.28. I'm doing the math wrong on this because I need to go up by about 4. And you see that goes to about 71 there because the coefficient for males is about negative 0.28. So you can solve this out for yourself and find out the coefficient of males. Why don't I do it, right? So the coefficient of males would simply be for their weight, would simply be for GPA would just be this minus this. We'll put in our negative right here. Why not? Reverse time. And the coefficient of males GPA would be this. And males would have predicted height. Sorry, I'm thinking about the variable. And then we'd put in here minus this. So minus minus. Why not? And we move that. And then we go right here. This would be times GPA. So this is GPA right here. And we go right here. And we grab the intercept. But one last thing we need to do. I don't care that got mad at me there. I'll repull up that code. I need to take the intercept and add in coefficient male and put that right here. I'm going to grab this. I'm going to put it here. And let's put this in. Oops, one more up. There we go. And there we go right there. If you notice, this line for males hits at this right here. I simply added in the 2 intercepts in that. And so I solved for the coefficient of males, which is barely above 72.1. And I solved for the coefficient of GPAs for males. And I can predict the height for males. And the predicted height of females would be very simple to find. And I should probably put predicted height male in this. Let me rewrite it. So this is predicted height of males. No, don't do that. Let's do males. Sure. And predicted height of females is simply, we go right here, and we would simply just take the values, and I've got them off the screen now. Just take the values that are available for you, like this right here, and drop it into here, because that's the reference level, reference intercept, and then the reference slope would just be this right here. And actually, you can see as I write this line, and this is going to be positive now. Please yell at me if I make mistakes, because I'm just doing this as I'm doing this. And you see here, this is the line for females. So we'll put them both on the screen. You can see the line for males is 72.1628 minus that, and the line for females is 64.45. So the relationship GPA has with height depends on somebody being male or female. For males, the relationship is negative and actually stronger. It's stronger because it's further from 0. And that's what strength of relationship is. Big tip there. Strength of relationship is how far it is away from 0. The stronger it is, the further it is away from 0. Strength of a relationship, really remember on your take home, hint, 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 isn't really dealing with statistically significant. It's dealing with how strong it is. And the visualization right here can show me the strength because I can tell this line is more sloped than this one. So I can actually look at visualizations to see strengths. It's like, oh, that's stronger because it's more sloped, stronger. And we're not talking about statistical significance. Strength is just like, what's the value of it? Like, what is its value? Like, its actual strength. And statistical significance, I don't think either of them were. Well, we only have one indicator, so this difference between slopes is not statistically significant, but the difference between intercepts is. So that's got it. Ask me those questions. I'm going to hang out for just a little bit longer. I've been on YouTube for 4 hours. You know what? If you want, you can smash that like or dislike. This is not my channel I try to grow. I'm sorry. I know I need more videos on this channel. I'm sorry. Petrie's got a bunch of great videos too. Everyone's going to hit that dislike. They're going to hit that F for dislike. So, yeah. So go ahead and ask questions, like or dislike the video. This video all of a sudden now gets thousands of dislikes. See if anyone's still watching. So, liked. Oh, well, thank you very much. So, I appreciate it, guys. Once again, I never put ads on any of my videos. I'm not trying to make, I think it says I can make $50 a year on YouTube. And some students have been like, why don't you do it? Because I fear it would interfere with the growth. I'm not trying to, make money on YouTube ads because I don't want you guys, if I make a 1-minute video, I don't want you to watch a 30-second ad, non-skippable ad on YouTube. So I don't want any ads on my videos ever. I'd actually be very unhappy if YouTube started putting ads on all videos. My videos should not have ads. I've never monetized either of my channels. So, or I got 4 channels, but a Stat 207 channel, which I don't know if that is it. No, I think I got 5 channels. I got 1 Minute Math, which has like 1 video. So I was going to make a whole channel called 1 Minute Math. It's like, learn how to do math in 1 minute. And I was like, this is my big idea. We're going to do 1 minute math. If you talk to me, like if you see me again in a year, be like, hey, Brian, what's your big idea right now? I'll have a big idea about like, oh, I'm going to do this. And some of you guys know my Twitch idea. So, yeah. Well, you could ask me about that, but God, what's your big idea? But ask a question if you got it. I'm gonna head off, eat something, and relax. But yeah, I thank you guys for all your hard work, and we definitely gave away a lot of the tests today.